Hello, I'm Robert, founder of Doomsday Debunked, which helps people with their fears of various scenarios by just explaining things as they are with no sugarcoating, just the truth as best as we know at present. And so this is about gamma ray bursts. And first of all, a lot of people are scared about that someday during the night, maybe while you're asleep, that these lethal gamma rays are going to hit you and harm you, or about muons. So first of all, I'm going to explain that you don't need to be scared of these things at all. But I'm going to start off with this particular thing that scares people. So many people do not realize quite how thick our atmosphere is and how much it protects us. So this is for the gamma rays. So if we have a look at this.
And we have 10.5 meters worth of...
So what I've explained is in this video, they are showing the amount of pressure in the atmosphere by trying to suck a red liquid up a straw. So have a look and see how far up you can suck it. And then when it's going up, what's actually happening is that you're creating a partial vacuum at the top. And the pressure of the atmosphere, the actual mass of the atmosphere, is pushing down on the liquid at the bottom in your glass. And then it's actually the atmosphere pushing it up. You're not really sucking it up. You're just creating a vacuum, and it's the pressure of the atmosphere. Whenever you drink something out of a cup with a straw, then it's actually the pressure of the atmosphere that is pushing that liquid up into the straw. So let's have a look and see how much.
Tubing, which goes all the way up to Nigel at the very top there.
So we're going to see if I can relive some of my former glory and get the red liquid up this height.
3, 2, 1. There you have, Nigel is starting to suck on that straw. There he goes. Looking strong. Create that vacuum. Approaching the edge of a cliff there. Go, Nigel, go! Come on, Nigel! Doesn't seem to be going anywhere. We seem a bit stuck. On that point right there,
You can see the determination, the focus.
trying to see how high that is. He's done well, but it just doesn't look like it's going to happen. Alright, so Nigel did pretty well there. We saw that he could get the liquid up that tube about 7 meters. Not the theoretical maximum of 10 meters. Still more than you.
So he got it up 7 meters, and the maximum you could get with a perfect vacuum at the top would be 10.3 meters, which of course you can't do just by sucking up the straw. So that is the amount. 10 meters of water. That's quite a lot of mass. That is what the atmosphere balances. And so that's how thick the atmosphere is. It feels like nothing to us because we have the same pressure inside. So the inside of your lungs have the same pressure as the outside. And you don't realize how much mass there actually is in the atmosphere. And luckily for us, the atmosphere is completely transparent in visible light. Depending on the atmospheric conditions, how much water vapor and so on, you can't see through clouds, but you can see through the atmosphere. But it's not really a luck or coincidence. It's because we have evolved to be able to see in the wavelengths that are where light actually can travel very far through the atmosphere. The actual particular wavelengths in which it's transparent. A little bit further into the higher frequencies and becomes opaque. A little bit further into the infrared, if you go a fair bit into the infrared, and again, then it's very difficult to see through it. Although you can see a bit in both ways, you can see a bit both ways. So gamma rays are well up into, and there are little windows into it, but gamma rays are well up into the very high frequencies, and it's completely opaque. You can't see anything. You wouldn't be able to see very far in gamma rays. Now you might think, oh, they're very penetrating. In X-rays, it's the same. Well, over short distances, they are very penetrating. But as they go, these very high energy things actually hit. It's because they hit different parts of our bodies in different ways that you can use X-rays to see inside our body. And all that energy means it gets very easily dispersed by the atmosphere if you go over any distance through the atmosphere. And the very high energy things like X-rays and gamma rays, we can't see them from the surface. And so until the first satellites, even though we could see X-rays and gamma rays perfectly well, but only over short distances, and the atmosphere, because it's completely opaque, we had absolutely no idea what the atmosphere looked like, what the universe looked like in those frequencies until we had our space telescopes above the atmosphere. So, when we had our first gamma ray telescope, then this is what it saw. You can see it got these flashes coming all over the sky. This was totally unexpected. Nobody expected to see anything like that when they launched the first gamma ray telescopes. And they were extremely bright. This is against a visible background. Is that gamma ray? I'm not quite sure what that background is, but this is the, I'll check that afterwards. And that's a picture of the telescope that did the thing. I think those green dots might be nearby gamma ray sources, because we do have soft gamma ray sources, but we have these extremely bright, and that's probably just visible light. I'm just guessing, because I haven't looked it up. But these big flashes were the surprise, and some were very short, and some lasted a little bit longer. And that's a notable one. So then they tried to figure out what those were, and there were two possibilities. They couldn't be in the actual plane of the galaxy, because that's where all this. They couldn't be just normal stars in our galaxy, or anything connected with those, because they would then all be clustered around in the plane. And they wondered at first if it was some kind of cluster of some objects that we didn't know about that were sort of in a spherical shape around our galaxy, but they found out eventually that they were extremely bright things from very far away. And it was a big puzzle for a while how this could work. But what they discovered is, and I forget which way do I go, the other way. I'm talking this a bit out of sequence for the actual article. So what they discovered was that they're in beams. These gamma rays are beamed out of certain kind of collapsing stars, and certain kind of things that happen in space can produce beams of gamma rays. And so when we see those dots, it's because the beam is pointed our way. When we see these dots, these flashes, that's a beam that just happened to be pointed towards us. And there are many more of them. That's only a tiny fraction of the gamma ray bursts in our universe. Many more that are pointing in other ways, and we just don't see anything because they're not pointed towards us. Now, there turned out to be just two types of these gamma ray bursts. They turned out we got this kind of hump-shaped curve when they bit like a two-hammed camel, and this suggests that the two populations they eventually found out that there were, and this is a similar diagram, and you can see one population in red, one in blue, and the blue population they think this is the observed peak energy. They tend to be a bit more energetic, and they have very much shorter duration, a couple of seconds or less. And the others are less energetic, less peak energy, but they last much longer, and the total energy is more. And they can last up to 100 seconds, even getting on for 1,000 seconds. So the short ones, as it turns out, these So these, right, first of all I'm going to talk about how we're not at any danger from the actual gamma rays themselves. So because we can't even see them in gamma rays, our atmosphere is very opaque to gamma rays, so we don't need to worry that anything's going to happen. And gamma rays aren't that penetrating either, they're fairly easy to block, but the atmosphere blocks them completely. And the other thing that people worried about were these muons, and so it turns out that these ones, which are much higher energy, are the ones that produce the muons, and not these ones. And when Philip Plait wrote his book a decade or so ago, this wasn't properly totally understood, and that's why he talked about there being danger from muons from the big ones. And it turns out that there isn't. That these ones are the only ones that can produce muons, but they have much less total energy, and so they can't really harm us with the muons. So So that whole muon thing that people got scared about is no longer a thing. It's no longer something you need to worry about. So there's no way, either way, that these are going to harm us in the middle of the night when you go to sleep and you're going to wake up all irradiated by muons. That was an old idea that is now known to be completely false. So now we have these two populations, and the small ones seem to be due to colliding neutron stars, and the big ones, the long ones, are because of the collapsing of a hypernova, a very, very large star, when it collapses into a black hole. So for different reasons, these produce focused gamma rays, and these produce more intense high-energy gamma rays for a very short time, and these produce less lower energy gamma rays for a much longer time. Now, the neutron stars, if we go around, see if I can find, it's up, I could go up for this one. So the neutron stars, I forgot about neutron stars. That's about how the formation of neutron stars, and they're both very distant. The nearest ones we've actually seen. The neutron stars. Oh yes. So I've got to show you my picture of the galaxy. There we are. There's our galaxy, and this is where the sun is. Of course, you can't photograph the galaxy from outside, and this is through working out the distance of the stars. We look from within, and we can see these various spiral arms, stars at different distances. We map them very carefully. We now know that ours is a bar spiral with not just a central hub, but we've got a kind of bar in the middle there. And so the sun is there. Now those colliding neutron stars, for them to be harmful to us because they're so weak, they'd have to be within, I think, 50 light years, less than a pixel in this diagram. The galaxy is really huge. That distance is 2,000 light years, and we haven't seen any of these even in nearby galaxies. The nearest galaxies for any gamma ray burst is they may have found nearer ones since then, but about 50 times the distance of the Andromeda galaxy. That's just because they're so rare. So, but we're talking an extremely rare thing. It's not at all likely to happen anytime soon. And if it does happen in our galaxy, then it could happen anywhere in the galaxy. Say we haven't even seen them in any nearby galaxies, never mind our own. And it would have to be somewhere in this tiny circle within that dot for the neutron stars, so we can forget about that. And so the only main thing now are the big ones, big collapsing hypernova things, and those are more dangerous out to about there, I think they say, about 8,000 light years, and that's two, so 1, 2, 3, about there, about that distance. They're dangerous. And we actually know 3 of them are to that distance, but they're all pointed away from us. So that's why we know that we're not at any danger from them. So the 3 ones are, and first of all, just to explain how it all works, then the gamma rays can't get through our atmosphere, but what they can do is they can damage the ozone layer and the upper atmosphere, and especially long duration ones. Then the ozone layer can be damaged for quite a bit damaged by those. And then that lets through ultraviolet light, and then the ultraviolet light then can potentially harm us. It can also produce, at the time of the supernova itself, then the ultraviolet light can cause surface layer ozone, which can be harmful. It can also, you get these interactions that lead to the formation of nitrogen oxides in the upper atmosphere, and then these over time, so this is the depletion of oxygen up above, that's destroyed by them, and this produces oxygen down below, and you get these peaks that are over time, and then they also create ozone. The gamma rays, not only it reduces the amount of oxygen ozone in the upper atmosphere straight away, it creates ozone depleting nitrogen oxides, which then work over a period of time. And then they, if it was in the South Pole, for instance, if the gamma ray burst happened to be pointed towards the South Pole most severely, then you get nitrogen oxides being brought down because you've got lots of downdrafts there, and then So I think those are nitrogen oxides in that graph, and then as that happens, and that leads to a pulse of ozone depletion in the upper atmosphere, and increases to ozone at the sea level, and that's because the depleted ozone up there means more ultraviolet gets through, and so then it starts creating ozone down at ground level. And this is the sort of thing that, and so if you had a burst from the direction of the South Pole, for gamma ray burst within a few thousand light years of Earth, then that could potentially lead to some increase in the ozone at ground level. But the answer was that there wasn't enough to raise the ozone levels enough to be harmful. We increased them to 10 parts per million, and we need to reach 30 parts per million to be harmful to life. And even if it all got absorbed in the sea, it wouldn't be harmful to ocean life. So this study disproved an earlier hypothesis that gamma ray burst could be the cause of the late Ordovician mass extinction. And it was actually falsely reported in the news. The news often get things very wrong, and the news said that this actually proved that they caused this extinction. It actually, the paper said the exact opposite. And so the other things as well. There's increased UV after the gamma ray burst, because it creates these ozone depleting nitrogen oxides in the upper atmosphere, which increase the amounts of UV, that life on the surface can get. But that is not enough to cause a mass extinction, and that you can easily protect yourself against UV. But we're not at risk of any of this anyway, so I'm not really quite sure why I'm explaining this. This is about a hypothesis from the past about ideas of how there could have been extinctions due to gamma rays in the past. But for us now, oh yes, I know why I'm explaining. If it was within 8 light years and it was pointed our way, then it could create these nitrogen oxides in the upper atmosphere, which could create the UV, which could then it wouldn't be enough to cause a mass extinction or harm at the surface. There wouldn't be enough ozone to be a problem, but it could have increased UV, and so over some period of time, then you would get more. You would have a heightened risk of skin cancer. You'd have to put more sun protection cream on, and you'd need protection from cataracts. You need to make sure you have UV resistant glasses. But I mean, as we turn out, so that is kind of the main risk for one that's sort of a few thousand light years away. And but as it turns out, we don't have any even of those to worry about. There are 3 candidates. There's one candidate which this is our very best candidate. Now, so another very complicated thing to explain. It's quite hard to explain all this because there's so many complicated things. Let's look for which are often misunderstood. And it's difficult when you've got these. Yes, here we are. So this is Eta Carinae, which is one of the only 3 of them known, and they're very easy to spot. Gamma ray bursts are candidates. A big star that is likely to collapse as the long ones, which are the dangerous ones. Then these have to be very big stars, so they're very easy to spot at a great distance. And so we now, I think they're pretty certain we know all the ones within 8,000 light years by now, because they're so easy to spot at a great distance. There was one, APEC was discovered not so long ago. And so Eta Carinae, that was been known for a long time. And this used to be one of the ones people were kind of saying, this is the one, mainly for the muons, the heavy electrons. But we now know that they don't produce enough of the heavy electrons to be harmful at this size. And it's completely covered in this big dust cloud, which would block the UV light. And this would have to be dispersed before there's much of a problem of that. So Eta Carinae, if I understand the research correctly, then Eta Carinae, it's no longer a risk to us at all, because it's covered by all this dust of the Homunculus Nebula. Now, they don't know which way it's pointing for sure. From the nebula, it looks as if it's pointing that way. It sort of makes sense that it is. But there's a remote possibility. It's very hard to see through the dust, and there could be a perturbing something else orbiting it, which would cause its axis to slowly precess, so that sometimes, maybe very occasionally, it's pointed our way. So it's not impossible that it could, but it's pretty unlikely that could be pointed our way. Indeed, if you just took 3 nearby stars and you pointed them at random, it would be extremely unlikely that any of them was pointed at us, because they've got whole 3-dimensional space to the direction to be pointed in, not just around the circle, but like that, or like that, or like that, in and up, upwards, or sideways in any direction. And remember that the most dangerous ones are the ones that are extremely narrow, like this, very narrow like that. And it's no surprise, that's what you'd expect. Even for 3 nearby, very bright stars, you would expect them all to be pointed away as by far the most likely thing. So anyway, for Eta Carinae, it is most likely pointed away. We don't know for sure, but it's covered in dust. What's more, Eta Carinae is extremely heavy, and at that weight, it is possible at the end of its life that it doesn't even produce a supernova, a very big star. All the big stars collapse into black holes, but a very big star can just collapse into a black hole so quickly that nothing comes out. The star is shining away, and then it runs out of fuel, it can no longer hold itself up, and just collapses into a black hole, and you just see it vanish. And it's no supernova at all. It might be that all we know, that when Eta Carinae reaches the end of its life, it just stops shining, and that's all we notice. So anyway, that one is not a risk. Now, there's 2 others. The 2 others. There's APEP, there's Eta Carinae, which I saw, and then there's WR104. WR104 is one that people used to get quite scared about. So this is one. It's I think it's an actual photograph of this, and it certainly looks as if it's pointing us face on, doesn't it? But when it did a very detailed study with spectroscopic observations, it turns out that its axis is at an angle around 30 to 40 degrees, and possibly as much as 45 degrees. So this image is a little bit misleading. It's not as dead on as it seems from that, and that would mean it misses. Now, another thing about this is that the gamma ray burst stars, most stars, even the very big ones, when they go supernova, they don't produce gamma ray bursts. We see lots and lots of supernovas, and it's very rare that they produce gamma ray bursts. So there's a question as to why is it that most stars don't produce gamma ray bursts. So we would, again, with 3 nearby ones, on just by probability, we'd expect none of them go gamma ray burst, but even at the end of their lives, but most likely millions of years from now. It's very hard to tell exactly when their life is going to end, and it could be any time for millions of years. So why do some of them produce gamma ray bursts? Well, it turns out if you look at the data, that it's generally in galaxies that have very little by way of heavy elements. When our universe formed, then way back, all we had was hydrogen, helium, and a little bit of lithium, which formed right at the beginning in the Big Bang. And then after that, as the universe cooled down, that's what came out. But then, after when it began recombination, when the first molecules formed, it became transparent to light. First atoms formed and became transparent to light, and molecules of the hydrogen. So when and then after that, it produced the stars and the galaxies, and then with the very earliest stars, very big stars go through their life very quickly, and then they produce a bit more of the heavy elements. For instance, all the oxygen in our bodies is made inside stars. So about the only thing that we've got from the Big Bang in our own bodies is the hydrogen, because you don't have much lithium or helium in your body. So and it's just hydrogen that comes from the Big Bang, and everything else that we're made of is made inside stars. And was made mainly, there's some other processes, but mainly stars are made inside stars during, like our sun is burning hydrogen into helium. Eventually then a star like ours can produce heavier elements, and it gets all the way up to oxygen, to carbon and oxygen and to nitrogen. And then other stars, other things like plutonium and gold and so on. All the gold that is made, I think the gold is made in supernovas. I would have to check this up. I've got an article about it somewhere about where the different elements are made. So some are made in supernovas, and so when this collapsing star and this hypernova, when it collapses, and it'll produce, especially if it collides to a neutron star, the kind of small ones, then the collision and then the bouncing away of the stuff into space, in that fraction of a second, it produces lots and lots of heavy elements, and a lot of like gold and stuff is made in that just tiny fraction of a second at the very end of a big star. I think I can add as a comment maybe which it is. So that article about where the elements are made. Anyway, so it turns out that gamma ray bursts are only tend to happen in galaxies that are very low. They have mainly just the hydrogen and helium and lithium and just a sprinkling of other elements, and these are the very earliest stars. And the astronomers call it metallicity. If it's got heavier elements than hydrogen, helium, lithium, they're called metals. Don't ask me why. I mean, oxygen obviously isn't a metal, but for some reason astronomers call these metals. So it's just a different use of the word. So anyway, these galaxies with a lot of the heavy elements, they don't tend to have gamma ray bursts. They tend to be only in the ones that got very few. So just by us being here, because we've got these bodies made with oxygen and carbon and stuff in it, then that shows that we're in the wrong kind of galaxy to be very likely to have these big, long, heavy gamma ray bursts. So this one, because it's in the wrong kind of galaxy, now you might wonder, why is it? Why would it make such a difference? It seems to be to do with the speed at which the star is rotating before it collapses. If it's got lots of heavy elements, then as it gets towards the end of its life, it blows off the gas as winds that blow off the equator, and the winds blowing off the equator slow it down and stop it from going too fast. But if it is a very old, very young with very little of the heavy elements, then it's just blowing off hydrogen and helium and a little bit of lithium, and that doesn't slow it down so much. And it has to be a very fast spinning star, so fast it's almost breaking apart from its spinning motion. And the just a little bit extra edge of having all these heavy elements that it throws off from the equator, that is enough to slow it down enough so as it collapses to a black hole, the equator isn't spinning enough. So it forms kind of accretion disk, and it has to be very fast spinning. And then as it collapses, the gamma ray burst comes out of the things falling into the black hole, and then things being sort of squirted out along the axis. And that whole process depends on the equatorial of the star as it collapses, spinning very, very fast. And if it's spinning just a little bit, not quite fast enough, then it isn't able to trigger a gamma ray burst. So it's very unlikely that WR104 would create a gamma ray burst, because it's in the wrong kind of galaxy and it's not pointed our way. So even if it did, it's not likely to hit us. So as a result of all this, the idea that we had past extinctions from gamma ray bursts is now not very, there's not a lot of confidence in it now, because we've got two problems with it. One, with the wrong kind of galaxy to have very many gamma ray bursts. It's not impossible, but they're going to be very rare. And then the other is that the gamma ray bursts have much less harm on the surface because of that detailed modelling that found out it wouldn't create enough ozone at ground level to be harmful, and because the amount of UV that you get, unless it's a very, very close gamma ray burst, then that's not going to be enough to cause mass extinction either, and especially in the sea, where you're blocked by the sea and water as well. So this used to be quite a strong hypothesis. It's now rather weak. I don't think many people think that we have had gamma ray caused mass extinctions in the past anymore. So now we go back to the third of our three candidates, and this is the only one that maybe has a decent chance of becoming a gamma ray. Where is it in the page? APEP. So APEP. Now, do I have a picture of it? Surely I have a picture of it somewhere. Where is it? I may have to go to this other. I'm sure I've got a picture of it somewhere here, but I can't seem to find it right now. I'll go to the other page. Oh yeah, there. No, is that APEP? And that is the. I don't seem to have put a picture of APEP in there. Okay, so I'll go to this one, and there we can find APEP. So this is APEP, and that is an actual photograph. It's a rather beautiful photograph. It's not an photograph, it's an artist's impression. So APEP turned out to be this star and another star surrounding it, and it's throwing off these dust gases, and then when they work out how it managed to produce, and you see that pose is the simulation, that they think is the same as that, and it's remarkably similar, the point where it poses. So they think they model it pretty well. And so from that modelling, then they are pretty certain that it's actually at an angle of, what is it, 40 degrees or 30 degrees, I forget now. Where does it say? 30 degrees. It's 30 degrees to the line of sight. In summary, figure 4, which is the one I just showed you, results from a spiral with a full opening of 120 degrees. The pole of the spiral is projected at 30 degrees to the line of sight, which results in some overlapping structures. So that is this model, and it's such a good fit of that and that really it seems pretty clear that it's actually pointed away from us. Now this one is very unusual, because the star, although it's a very heavy star, it's spinning much faster than you'd expect. And they think and that's partly why it produces this dramatic structure, because it's got very, very fast. I think it's 1% of the speed of light that the gas is being thrown off at its equator. It's spinning it extremely, extremely fast. And the reason may be, and it's just almost on the point of breaking apart, because it's spinning so fast. And they think that it may be because of two stars that collided to make this fast spinning star. And this situation of is a very young star as well. And these are very young stars that do these huge things, because they just don't last very long. You might think a big star would last longer. It's the other way around. A big star doesn't last very long, because it burns up its fuel so very, very fast. And it just lasts tens of millions of years, some of the biggest stars. And before it reaches the end of its life. So somehow, and they think that there are probably two very young stars, right in very early time in their life, they actually collided with each other and combined together to make a single star. That is a very, very rare thing to happen. And so this is a very fast spinning result of the collision of two very young stars plus a third star. And in this very unusual situation, then it can be spinning so fast as to produce a gamma ray burst in our galaxy. But we only know of one example of this in our entire galaxy, and it is not pointing towards us. So that's all three of the ones that are close enough, and we just don't have any gamma ray burst candidates that are close enough to be able to harm us in any way, even just damaging the ozone there. Then we don't seem to have any that are close enough. So this, if I'd been giving this talk a decade ago, then I would just have to say probability. I would have gone up to this thing and I said, look, we haven't seen any in our galaxy yet, and the nearest ones are just so many galaxies away, and just extremely rare, and I would have tried to come up with a number for how unlikely it is. But now I think you can say that for these very big ones, the hypernova ones, then it's just not possible. With the only three at a distance of about 8,000 light years, the only three, and they're all pointed away from us, and only one of those three is even likely to produce a gamma ray burst. We do have one possible candidate for a gamma ray burst, but it's pointed away from us. And then the small colliding neutron stars, they're just so very rare, and they're weaker, and they're just as far away as the others. We haven't seen any of those now. They're about 50 galaxies, 50 times distant to our nearest galaxy as well. So you don't need to worry about gamma ray bursts.